Hey everybody, welcome back from spring break, and we're going to take a look at Notebook 13. So if you need to pause the video, that's fine. Go ahead and go to the course calendar and load Notebook 13. All right. And if you need to, like I said, pause and get ready. So we're going to be talking about hypothesis tests. Okay. And what that means is we're going to simulate a sampling distribution. Sampling distribution is where you take repeated samples of the same size. And in this example, we're going to find the median of each of those samples. And then we're going to keep a collection of those medians, and that's going to be our sampling distribution. And we can do this thousands of times and get a more and more accurate picture of what the distribution looks like. And so the idea is that we're going to create an estimate, right? So we're going to estimate the actual median. And the law of large numbers, as we've talked about before spring break, was that our estimate will improve. We'll get more and more accurate as sample size increases. Why? Well, because the bell shape of the histogram is getting narrower and narrower. And you'll see visually what that means as we go forward. All right, so let's hop into the notebook. Sorry, let me scroll back up. I've already initialized, but make sure we run the initial code block. And we're reminded in the first instance about the lady tasting tea example where Dr. Ron Fisher gave a taste test to Dr. Muriel Bristol, and it turns out that she was able to identify all 8 cups of tea based on whether the tea was added first or the milk was added first. Okay, so what we're going to do is we are going to simulate this many times. And let's just talk about what this code is doing, this code that I've highlighted here. Okay. Sorry. So this was a little bit earlier. I'll cover it right now. So take a pause. Level of significance. So this is alpha. This is a lowercase alpha. And level of significance is the cutoff value that lets us know what are unlikely probabilities. And setting alpha at 0.05 goes all the way back to Ron Fisher and the lady tasting tea. And it was traditional, but it turns out that it works really well. So occasionally, alpha may be set to a slightly different value, but especially in this elementary applied statistics course like this one, 0.05 is going to be very typical. Okay, so every hypothesis test that we run is going to give us a p-value. And maybe I should put quotes around this because it's not exactly true, but a good idea of what the p-value is it tells us the probability that the null hypothesis is true. So when we have a p that's smaller than this alpha, we get rid of the null and go to the alternative hypothesis because the null is unlikely. Okay? So we will be going through these ideas and make them more explicit in just a few minutes. So let's jump in here to what in the world did that code do? All right. So we're creating a coin, and you're like, wait, I'm used to seeing heads and tails. Coins don't usually have zeros and ones. Well, this is saying that, hey, we're going to pick one, and I don't know, maybe it's tails, and then every time it comes up tails, that's a success. So the success is labeled 1 and the failure is labeled 0. And again, either heads or tails, whichever, the coin flipper's preference is. Okay, and then what's this 10 flips thing? Well, it's an array created by this np.random.choice. It's going to select an outcome from the coin 10 times. And what does replace equals true mean? Okay, well, that means that when I've drawn it, it can go back in and be drawn again. So it's easier to understand or at least for me, the replace equals false is like dealing from a deck of cards, because once somebody has been dealt the ace of spades, nobody else can receive that card. Now, replace equals true would be if more than one person could get the ace of spades, right? If after it was dealt, another copy of the ace of spades was replaced in the deck, in the thing that's being dealt from. Okay, well, all we're saying is that here is that after we've had a success, we're still drawing from the exact same thing, right? So we can have 2, 3, 4 successes in a row, even after they've been drawn. All right. And so then we have this 10 flips, which is just a series of zeros and ones, depending on whether that simulated coin flip was a success or failure. And then, sum the 10 flips. Oh, so again, 10 flips, let me just draw it in real quick, right? So 10 flips is actually going to be an array, and it's going to have, zeros and ones, and all the zeros are failures, all the ones are success. Okay, and I'll just go dot, 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 right? So the random choice creates this array, and then when we sum it, obviously adding up all the zeros doesn't add anything, but the number of successes out of 10 is added up when I do the sum of the 10 flips array. Okay, so let's take a look at what this actually looks like in practice. Sorry. Okay, and as you see that I am executing this multiple times, and it went 3 and then 5 and now 6, right? So every time I execute this code block, it simulates flipping a coin 10 times and recording all the successes. Again, let's just say that we're looking for tails. And every time it comes up tails, we put in a 1. Every time it comes up heads, we put in a 0. And then we sum them up at the end to get the total that were successes, okay? So this is the total successes out of 10 coin flips. And there's a bunch of 5s. Oh, there's a 7. So again, every time I do this is going to be slightly different. Now, don't worry too much about this. This sets the random number generator the same for all of us so that we can do this example and we should get the same results. So I'm just going to run it once, okay? And let me do that, okay? And then times right, okay? So here, the repetitions is 5,000, okay? And so 5,000 times, it's gonna do this 8 flips, which is just like the 10 flips up above, okay? Except it flips a coin 8 times, and the times right out of 8 is what it records, okay? This NP append just puts the times right on the end, okay? So basically this times right, I'm sorry, this is an array, this times right, and then the result from 8 flips is put on the end. And then I have this big array called times right, and they're doing the exact same thing here that they were doing here. If I sum up all the times right, all the time that times right is equal to 8, we're going to count up how many times we had a perfect score, that we flipped the coin and it came up all heads or all tails, okay? And then we're going to calculate this p-value, right? What's the probability of over 5,000 times, how many times out of 5,000 do we get all 8 of these coin flips correct? Okay, so flip it. So we're doing a couple things here. It's showing the number of correct guesses, and you see that sometimes we get very few right, maybe only 1 correct. And it is pretty common to get 4 or 5 correct out of 8, which makes sense. And it's less common to get 6 or 7 or 8 correct out of 8. Okay. And then down here, we've actually, see, we calculated P up here, but we didn't print it. And if we print P here, sorry, we get P equals 0.0022. Okay, so we have simulated 5,000 times of flipping the coin 8 times and counting how many successes there were. We did that 5,000 times. That resulted in this simulated distribution. And the probability of getting all 8 correct, and again, this is the lady tasting tea, is about 0.22%. Okay. And since it was low, we concluded that she wasn't guessing, right? So remember, the p-value is the probability that the null hypothesis is true. And what Ron Fisher's null hypothesis was, hey, let's just assume she's guessing at random, that she can't really taste the difference between the two different ways of making tea, and she's just guessing. And then the probability of success would be 1/2. And if that were true, we just did it. We just did a simulation of 5,000 times to verify that the probability, the empirical probability, is about 0.22%. Since that's really unlikely, that's less than 0.05, which is what Ron Fisher was using, but it's less than 1% even. So we reject that idea because it's unlikely. And if we're going to reject the null hypothesis, that means the alternate hypothesis is what we're going to have evidence is true. And so we have evidence she was not merely guessing, but she was actually able to identify the correct answer to a value greater than 1/2. And again, this is what I went over on the slide. Level of significance is alpha. It's usually 0.05. And when p is less than alpha, we say the result is significant. Okay. And since the outcome that actually Dr. Muriel Bristol actually got 8 out of 8 correct, and since that probability we calculated was way, way less than 0.05, we conclude that the alternative hypothesis is true, that she was not guessing and she could taste the difference. Okay, so now we're going to do the same thing, but we're going to grab this table of salaries from San Francisco in 2015. So these are San Francisco city employees, I believe. And we're going to go into the total compensation column. And we do set a minimum salary, so part-time workers or whatever, they're not going to be included. All right. So let's load the table. And then we're going to calculate the median. Why? Well, this is the population median. And this is a huge table. And why are we doing it? Well, and then here, what's going on here? Here we're doing it by hand. There happen to be an even number, so the median is the average of the middle two. And so we've taken some time to figure out what the middle two are. Okay, but this is the population median, $107,518.63, but basically 107,518. Okay, so now what are we going to do? Well, there are a bunch of these, almost 40,000 of these individuals that work for the city of San Francisco. And so what are we going to do? We're going to take samples of size 300. Okay, so you see this sample 300 with replacement equals false. Why? Because as soon as we've grabbed somebody, we don't want to have 2 copies of the same individual in our sample. If we've drawn them, we're going to keep them. So it's like dealing from a deck of cards, right? Once we've gotten one of them, there's not another copy. Okay. And so, of course, they just show us an example. Okay, so here is, 300. And if you scroll down, oh, it showed 5, and there are 295 rows omitted. Okay, so we've got, the department they're in, and, all these things, family code. And then the key thing is that we also have this total compensation column, which is where we're going for the median. All right. Now, so MP percentile, our sample dot column, total compensation. So we're grabbing the 50th percentile of the sample. Now remember what this did, the sample is only 300. So there's almost 40,000 in there. So we do a random sample of 300, and what do we find? We find the median is 108,981. Now remember that we know the actual median is 107,518. So this is off a little bit, okay? And here we go. So now what are we doing? We are making a histogram of the total compensation column. Okay. And this is what the population looks like, the distribution of the population. Now it's not bell-shaped, it's a little weird over here on the left. Now the right-hand side of this bell curve, or excuse me, um, candidate bell curve, right? It's very bell-shaped over to the right. Over to the left is a little wonky. What happens here? Well, we're doing the same thing, but now we're doing a histogram of our sample. And notice that our sample looks a little bit like the actual distribution, but we've only taken one sample of 300, so there are some differences you can see. Okay, and what we're trying to help you understand is that each one of these samples is going to be a little different. There's some variability here in these estimates. Okay, so what's going on here? This is just running the sample using some defined sample size, right? Which is going to be posted by the person in the when they call this function, and it's going to find the median. All right. So sample median equals, and this is calling it, right? So we've defined it up here, and then this calls it, and it should work. And every time we do it, we should get a different median. Why? Because it's taking a sample of 300 and it's creating a median. There, the median was of that sample was about 103.7 thousand. This is 109,000, almost 110,000. There's 112.5 thousand, about 104,000. So every time we generate this, this is different, and you can see that it calculates there. There we're almost 3,000 below, minus 2919 below. Wow, that's kind of close. That's only $408 off when we took that sample. And so these are just showing you that yes, every single time we do this, we generate a sample median by selecting 300 individuals from the list at random and then taking the median. And there is some variability of the estimate, that is true. Now what we're going to take a look at is how do we get these estimates from simulations? How do we get these p-values and estimates? And so you're going to see a bell-shaped histogram, and I'm just drawing the envelope of the top of them. And there's going to be a gold bar down here that shows how we use the distribution that's being shown to us in the histogram to create an estimate. All right, and so the gold bar will be, will actually show a picture of that estimate. And so the idea is, let me just say that whenever we're estimating in applied statistics, you'll hear this word confidence interval. So we often use the middle 95% of the simulated distribution. And when we do, it's called a 95% confidence interval. All right. And as the law of large numbers says, sample size increasing will indicate that our estimate will improve. Okay, let's go back to let's go back to our notebook. And sample medians, so this is going to do it 1,000 times. That's what this means, this for I in NPA range 1,000. Basically, it's going to run this 1,000 times. It's going to generate a sample median from 300 observations. It's going to do that 1,000 times, and it's going to keep a list of them. All right. And then sorry, I'm trying to get there, right? Then we can see these. And by the way, there is a little red dot there. It's really hard to see, but inside this circle that I'm drawing, there is a little red dot. Why? That's the population median. And the whole point is that this bell curve, right, is going to be centered, and I'm sorry, I drew it very poorly, but it is going to be centered near, the center of this histogram is going to be near the actual population median. That's what we're estimating, and that's what we're going to get close to. And just notice that it's slightly different every time. There's another time, all right? And we do it 1,000 times, and notice that every time the histogram comes out near this median. Okay, so what are bootstrap medians? We are going to repeatedly draw these samples of the same size, and right, the sample size there is 300, and we draw them, and you can see that the bootstrap sample, and it is somewhat reminiscent of the old distribution that we had. Okay, and give it just a second here. And what's going on? Well, okay, so the red is the population median. So that's the actual 107,518. And our estimate, the median of in here is in blue. So again, our blue is trying to estimate the red, and you can see that when we did this, you know, hundreds and hundreds and hundreds of times, we're getting very accurate. And this is the same exact thing, except it's showing, oh, this yellow bar here, that's the confidence interval. What are we doing? We're saying, hey, 95% of the observations in this distribution fall between the two red vertical lines that I drew, right? So we're saying, hey, we're pretty sure if we're trying to estimate the median, we're pretty sure it's in there where the gold bar is, okay? And sorry, let me erase those lines. And then what can we do? Here, they're actually showing you what we're doing is we're taking this, these bootstrap medians, right? And we're finding the 2.5 percentile. And by the way, I don't know how I got that. There's a space in there in mine that shouldn't be there. And then it's also finding the percentile, the 97.5 percentile. Think about it. If you subtract 97.5 minus 2.5, you do get 95%, which will give us the middle 95% of this distribution. And when I do that, you're going to see, oh, the gold bar then is showing the middle 95% of the different medians that were in this bootstrap sample. So that gold bar is the confidence interval. Okay, now we're doing the same thing, but we're doing it with means. Okay, and what are we seeing here? Right, we're seeing where these actual means are. Okay, so red is here and blue is here. So we're kind of way off to the right a little bit. All right, let's try it again. Sorry. Um, and so here is the confidence interval estimate. All right. And one last time. Right, and so you can see this is what it means. We create a simulated distribution, and that allows us to have an interval along the x-axis which we can use as an estimate of where that population mean or population median actually is. So that's all we've got for today. I do want to remind you about the law of large numbers. That's why we're using a computer to do hundreds and hundreds and hundreds of repeats of the same experiment to improve our estimate. Okay. And I do also want to mention that I'm going to make a separate video to help with your completion of Lab 6. Lab 6 and the extra credit homework 5 are due this weekend. I hope everybody has a great weekend. I will be back to you soon.